Hey QED coders, Michael L. Perry here. We talked about the pattern for storing mutable properties without doing updates or deletes. Now let's talk about idempotency. Why is idempotency important? Well, in a distributed system, I'm going to have different clients talking with the server, and they're going to be sending messages to the server. The client can't tell if the message didn't get to the server or if the response didn't get back. The only thing that the client can tell is whether or not it received a response. So let's take a look at this example. We've got one client talking to a server, and it's going to send a message. Let's suppose that the first time it tries, the message fails to reach the server. There might be some sort of network timeout, some sort of hiccup, whatever the problem is. The message didn't reach the server, and so the client is sitting there waiting, trying to receive a response that never comes. So the client has to be able to retry, make sure that that message gets to the server. So the second time it retries, it sends the message, it gets to the server, but then the response doesn't make it back. Again, same sort of network glitch could happen. And so the client can't really tell did the message get to the server or not. All it knows is it didn't receive a response. So it has to retry again. It doesn't have any other choice. So the third time, let's suppose the message makes it through. The message gets to the server, the response gets all the way back to the client, and now the client knows that, okay, the server heard the message. So it can stop retrying. But notice, the server has heard this same message twice. We have to make sure that the server doesn't respond any differently the second time than it did the first time. And that's why it's important to be idempotent. So what is idempotency? Well, there's a formal definition of idempotency that's based on functions. Let's suppose that we've got the state of the system represented by a variable, we'll call it x, and then we apply a function to change that state, so the system is now in a different state. And so that change to the state, we'll call that the function f, and so the new state will be f of x, that change applied to the state of the system. So if something is idempotent, that means that if I apply that same change twice, I should still be in the same state as if it had applied it once. So we can define that formally by saying that f of x is equal to f of x. That's the formal definition of idempotent. Let's see what it looks like visually. Let's represent the state x as this bubble. So this green bubble means that the system is in the state x. I apply the function f, and that takes it to this blue bubble, f of x. Now, if I apply the function f a second time, the state of the system should still be blue. I shouldn't change the state just because I've applied the same function twice. So that's what an idempotent system looks like visually. Now, in a distributed system, you don't just have one client. Sometimes you've got two, sometimes you've got many clients, all trying to collaborate at the same time with the same server. So what does idempotency look like in a multi-client situation? So here we've got our server, and now instead of just one client, we've got two clients trying to send messages to the server. And so they're trying to apply changes. So we start at state x, and then one of the clients sends the message f, and that transforms it into the state f of x. Let's suppose that the response doesn't make it back to that first client, and so it's going to have to retry. But before it does, the other client sends a different message, g. So that transforms the system to g of f of x. So I've applied f to x, and I've applied g to that result. So now I'm in the state g of f of x, and then the first client retries f. At this point, I want to guarantee that f, even though you've retried it and something else has changed in the meantime, doesn't change the state of the system. So here, I want to ensure that f of g of f of x is equal to g of f of x. In other words, that the function f has no additional side effects, that it doesn't make any additional changes once it's already been applied, even if something else has been applied afterward. So this is a stronger definition of idempotency, but one that's really important in distributed systems that have many different nodes collaborating with one another. Now, let's go ahead and take a look at how updates fare in idempotency. We already talked about how updates destroy data. Let's put that aside for a second and just focus on idempotency. Update is idempotent. So let's take a look at an object that's in the initial state where the name is equal to Joe. Now I want to apply an update to that object, setting the name to Joseph. Okay, so now we've got this object in the state name equals Joseph. If I apply that same update a second time, it'll have no effect on the object. The name is already Joseph. So updates themselves are idempotent. But updates do not follow the stronger definition of idempotency that's important in a distributed system. So if one person is trying to update the name from Joe to Joseph, and another person is trying to update the name to Jim, then we might end up in this situation, where I apply the update to Joseph first, and now I'm in the state name equals Joseph, and then I apply the update to Jim, so now I'm in the state name equals Jim. If I try to reapply the update to Joseph, then the update will go ahead and take, and so now we'll be back into the state name equals Joseph. So we are not strongly idempotent here. We are not ignoring the second attempt to update the name to Joseph. We're actually applying it. So we're no longer following the identity that f of g of f of x is equal to g of f of x. So let's compare updates to historical modeling and see how we fare. We'll start here with a person and the name equal to Joe. Now we want to apply a change where we change from name equals Joe to name equals Joseph. And we capture the fact that name equals Joe was a predecessor of that fact. Now some other client comes through and it says, no, the name isn't Joseph, I'm going to change it to Jim. So now we've got this fact here where the name equals Jim and the name equal Joe is a predecessor. So we've got that linear history. If we then try to reapply name equals Joseph, we know what the predecessor is. The predecessor is name equals Joe. And so trying to reapply that fact, we say, oh, we've already got it. So we do nothing. And so with historical modeling, by keeping track of the predecessors, we can make sure that we don't reapply an update when it shouldn't be reapplied. We can be strongly idempotent. If a client truly wanted to change the name from Jim back to Joseph, then that would be a different change altogether. That would be a different predecessor and a different successor. And so that would be captured and it would be applied, but it would be different from the original one. Keeping track of the predecessor helps you to keep track of what the history should be. It captures the true intent of the change. Now, we can't talk about idempotency without also talking about rest. So, in the next episode, let's come on back and see how historical modeling and rest play into each other. So, come on back.